Okay, so by now you're pretty well versed in this whole derivative of the outside while keeping the inside the same, multiplied by the derivative of the inside function. You've done that a lot. But there's this other bit of the chain rule that comes up, and it always sneaks up on me. And then I'm like, oh, look, it's that other thing. So this other thing, we're going to just put that aside, is this weird looking equation, dy dx equals dy du times du dx. And it's like algebraically, you can look at that and go, well, yeah, that fits. Algebraically, the du's, we can cancel them out. So yeah, that fits. So really you're just saying the rate of change of y with respect to some variable times the rate of change of that variable with respect to x. So the best way to see how this works is to see an example. In this situation, this weird version of the chain rule, which doesn't even look like the chain rule, it usually shows up in story problems. So I've created a story problem for us, and it's dealing with the totally real creature of the Kraken. Kraken? Whatever. So let's say that the length is just a linear function. It's 3 plus 2t, where the length is in centimeters and time is in months. So a newborn would be 3 centimeters long. Are they born or do they hatch? I don't even know. Okay, and let's just say that the volume is half of the length cubed. So the volume would be in cubic centimeters since L was in centimeters. And yeah, I've just totally made this stuff up. Whatever. So given that the length depends on time, let me back up. Since volume depends on length, so V we get from the length, but the length depends on the time, is it reasonable then that volume depends on time? So basically what we could say is that volume is 1/2 of L, which is, we know it's 1/2 L cubed, but L is this 3 plus 2t. So 3 plus 2t. So if we know the time, the age of the Kraken, then we know the volume of it without having to calculate its length. And we could figure out how fast that volume is changing as time goes by taking the derivative. So dv dt, I'm going to use this notation, the dy dx notation, because we have so many variables going with L's, V's, T's, all that. So we'll stick with this notation. So it's saying change in volume over change in time. So we get half times 3 times chain rule here, derivative of the outside, keeping the inside the same, times derivative of the inside. This time I am going to clean it up. So just to make this a little bit tidier, the half and the 2 cancel out conveniently, so we just are left with 3 times 3 plus 2t quantities squared. So there's another way we could get to this, though, the rate of change of volume with respect to time. And this is where this weird version is going to come in. So we know L is 3 plus 2t. Just copying that down. So dl dt is just 2. We also know that V is 1/2 L cubed, so dV dl is 3/2 L squared. So that means that, now looking at this, if we want dV dt, we can take dV dl and dl dt and multiply them. Because now those dl's cancel, right? And so dV dt equals dV dt. That's kind of weird looking. And now we can replace dV dl with what it equals, the 2. We can replace dl dt with what it equals, which is 3/2 L squared. And so we have dV dt equals 3L squared. But wait a minute, that doesn't make sense. We have dV dt, t. Shouldn't this be a t? It doesn't fit. dv dt equals this thing, dv dt equals this other thing. Shouldn't those be the same thing? Well, yeah, they actually are, because L, remember, is 3 plus 2t. So I can substitute that in. So dv dt is, oh wait, this exact same thing. So it's just two different ways to get to the same thing. And the whole thing is just an example of a problem that it sneaks up on you, and like I'll be sitting there going, okay, I need dv dt, I need dv dt. Oh wait, I know dl dt, I know dv dl. I can put it together, oh, chain rule, and make it all fit. So that is our part 3, the weird stuff version with our Kraken, to give us our chain rule part 3. And we're done.